Thanks, everybody. I'm going to try and keep this upbeat. There were two questions in that quiz that I posed, and I can see the look of horror on people's faces. And within the context of the other questions, yeah, they were a bit daunting and a bit hard and a bit depressing. But anyway, disasters. Here we go. This is work I'm doing at Oxford, but I'm connected with the Alan Turing Institute and also with the Satellite Applications Catapult. The Alan Turing Institute and Satellite Applications Catapult are very much focused on applications, transfer of knowledge to the real world, solving big world problems. My research, let's go on to this one first. So let's discuss disasters first, and I'll tell you about my group in a little bit. So there's a whole bunch of them. So we have floods, yay. We have tsunamis, cause a lot of damage. We have landslides. We have tropical storms, cyclones and so on, forest fires, heard a lot of those recently, heard a lot about those things. Epidemics, these are more the natural disasters, and then we get human ones, deforestation, hope you're all feeling inspired. Pollution in the oceans, which is incredibly gross, and then we have haze. And to really bring these disasters closer to home, let's look at air pollution in London. So, answer to one of the quiz questions, how many people die in the UK every year due to air pollution? It's 40,000. Air pollution leads to heart disease, lung cancer, the belief now is osteoporosis, and so on and so forth. Actually, 40,000 is the lowest estimate. The Europeans came up with 64,000 in the UK. And if you have a look there at where nitrogen dioxide, I think it is mostly concentrated, it's right where we are now. Yeah. So I hope you guys are good at holding your breath, or you held your breath before you came into London and you're still conscious and so on. This is a big problem for the UK. It's something we really need to get sorted. So next time, leave your cars at home and bring your bikes in, because cars, industry and so on, these are the main contributors to air pollution. Anyway, okay, that's my lecture for the evening. Now get back onto the talk. So a lot of people don't like this diagram. It's the disaster cycle. They say it sort of partitions things a little bit too neatly, but this is more about sort of who takes control, different parts of the cycle of a disaster. So you begin with mitigation. So you try and remove as much as you possibly can any kind of possibility of disaster, by understanding the hazard, by making sure that you build buildings in places where the hazard doesn't exist, for example. Then you've got preparation. There's a disaster on the horizon, or at least there's a hazard that's building up, and you might want to move people out of the space where that hazard is before it kicks home. Then a disaster occurs, or the hazard has kicked off, and you want to go in there and save people after the event has occurred, and then the disaster's finished, or the hazard has sort of subsided, and then you want to recover from that disaster, rebuild schools and all this kind of stuff. AI, machine learning, can be used in each part of those, of that cycle, and general ideas around situation awareness. You understand what the situation is on the ground right now. Predictive analytics is about sort of predicting forward to try and mitigate things, to try and improve the way in which you recover, and so on and so forth. And risk analysis, uncertainty, is inherent in everything that we do in disaster management. I'll cover some of these areas via examples going forward. Now, I talk about my group. So it's a very small group. I've got a postdoc and a PhD student at the moment, and today my postdoc's husband joined the group, which is amazingly good. He's here for 2 weeks working on seismic faults. I'll tell you about that in a short while. So one of our main data sources is satellite imagery. So I'm going to be talking a lot about satellite imagery, but a lot of the work we do in machine learning can be transferred to different data sources as well. And I'll try and come up with analogies with other data sources as we go on. Focus is on disaster management, environmental protection. These are the two domains that get me up in the morning. So I'll say I've been machine learning for 25 years, developing foundational machine learning, applying it to a whole bunch of different domains. But these are the two domains that really grab my heart and really motivate me. And when the going gets tough and I think, oh, why am I doing this? When I see what the end consequences can be, I keep going. Been lucky enough recently to work with the UK Space Agency, work with organisations where the end result is is to deliver something in the real world. And these organizations help us to co-create. The Alan Turing Institutes like this helps us to co-create with the end users, to co-design with the end users. And a new word I like to use is co-research with the end users. So once you've actually proved that you can deliver something, then you go ahead and do research with the end users in such a way that you know that the product you come up with is going to be of some use to them. But right the way back to, to the research level, actually starting off with that fundamental problem description that you know that the solution will ultimately lead to something of value in the world. So there's 4 examples there of little projects that we were doing with Satellite Applications Catapult. And this was working with various UK commercial organisations and others to deliver solutions in Malaysia. So the Malacca Straits, it's one of the busiest shipping lanes in the world, and there's lots of oil pollution there. A lot of work's already been done on the diffusion process of oil, but the key question is where's the oil come from? This is a machine learning problem. So we've been developing techniques that will very efficiently determine out of the thousands of ships where the oil could have come from, which ones to rank, which ones to look at. And what happens is, for example, once you've determined a few ships, the authorities will go onto the ships, collect the chemicals from the ships, and then they'll collect chemicals from the oil spill, and then compare them, chemically, and then determine the actual source of the oil. Rainfall nowcasting, so this was determining the rainfall, looking at cloud heights, so using satellite imagery to look at the clouds and determine the amount of rainfall. We needed to calibrate this method, so we used little rain detectors on the ground. But these rain detectors are notoriously, fragile. So one example is, the wind can blow in different directions and the rain gauge will misread what's going on. Or you'll get the farmers going out there and sticking a brolly over the rain gauge and shouting drought and so on and so forth. So this then was a problem in anomaly detection and error removal, which is another machine learning capability. Looking at floods, the third one along there, what we've got is an area represented by about 1 million pixels, and the flood going on in that area. And flood is a product of a neighbourhood to do with topography, to do with land use, and all this kind of stuff. And each pixel has got a bunch of parameters associated with it. And our flood experts wanted to learn the parameters, what the parameters were. 1 million parameters, well, more than that, maybe 3, 4, 5 million parameters. That's a tough problem. That's another one that we've been able to solve using deep learning, which Simon mentioned earlier on. But the one I want to talk about today, which will involve hopefully you guys going forward, where you can actually help to solve some disasters here, is this thing at the end, where we're combining humans and computer expertise together to provide situation awareness for our disaster response organisations. Right, quick look at where satellites are used right now to help in disasters. There's been a huge growth in that sector recently. The blue dots, which sort of dominate, these are the kind of flood water related disasters. You see some of those in the UK and so on and so forth. And then there are others to do with the geophysics and all this kind of stuff. Bottom right shows where the kind of growth industry is in satellites right now in this space. You can see Southeast Asia is one of the dominating markets, if you want to put it that way. So, there's a great opportunity there for us to grow our satellite industry and sell it in those spaces. Right, so it's not only satellite imagery. We can play about with tweets, we can play about with a whole bunch of different kinds of data sources. But what's important or of interest to us in the university are these unstructured data sets. So an unstructured data set means that there's no existing model that allows us to extract the information from the data. And what we need to do is construct that model dependent upon each data source, and often within the context of each data source as well. And you can see there the amount of data that is available after an event, 177 million disaster-related tweets. Imagine going through all those, trying to figure out what are important ones and all this kind of stuff, and keeping your hair on and not slitting your wrists or anything like that. Nightmare. Same with Caribbean disaster that was mentioned in the quiz in 2017. There was at least 11,000 kilometres squared of islands there that needed to be investigated after the hurricanes blew in. I'll talk about those a little bit going forward. So, before I dig deep into the technology, I'll just introduce you to partners that we work with. This is Rescue Global. It's an NGO based in the UK. Ex-Special Forces guys. They drop into areas that are generally hard to reach following a disaster. You'll see them skydiving in a bit. And then they do reconnaissance, and they gather information from all over the place and data from all over the place, collect it all together, and then pass it on to NGOs, government organisations and so on when the disaster response is being planned. They also deliver aid when they have time. They're really into technology. They can create their own cell network. So one of the important things is to get people to communicate after a disaster, the locals to communicate. The real true first responders are the locals, because they really know their environment and how to respond to environments and so on. They have interoperability capability, so they work and also coordinate other organisations, and they also help out and advise in local environments. So we've been working with these guys now for about 4 years, and after a tremendous amount of we've developed a tremendous amount of trust really by working with them on a whole bunch of working with them in a whole bunch of different kind of ways. So first of all, they will help us to connect with in-country partners, which is important. So the in-country partners trust Rescue Global, and Rescue Global trust us, and it's like there's a connection generated from that. We write publications together, which is really good. So they've really got into the whole mentality of academia. We've entered into social science a little bit, and this is one of my bugbears. It's kind of practical social science we want. We need to engage with end users and so on. We need to understand the culture of countries and so on and so forth. I'm in machine learning. It's not really my remit. But we need social scientists to join us, but I'm not academic social scientists. We need people who are practically able to analyse situations there and then and help us engage properly. So we've done ethnography with these guys. We've gone off on exercises and so on and saw how they used their technology. We also did some, I call it extreme ethnography or embedding and so on. So I actually went skydiving with you guys. I think they misunderstood by what I meant by impact-driven research. The aim being really to deliver products. I suppose me hitting the ground is some sort of delivery of a product. But anyway, I'm still here to tell the tale. Most important thing I think we've done with them is operational support. So we do the science, we develop the science, but then we work alongside them when there's a disaster to deliver information that they need. So how does that work? Well, we created this thing called the Planetary Response Network. So anybody here heard of Zooniverse? Yep. Wow, brilliant. Cheers, mate. So Zooniverse is the world's largest crowdsourcing platform. What do I mean? Well, I'll show you what I mean by that shortly. Just keep Zooniverse in the back of the mind for now. But Zooniverse platform involves you guys, the crowd, and a bit of machine learning alongside to take the data that you guys provide, and then we turn this into what's called heat maps. So heat maps, you've got a map of an area of interest, and then it's coloured according to some kind of question that is posed to us by the disaster response organisation. So they might want to know where there's building damage. So we'll put maybe red squares where there's building damage. Damage proportion, 20%, 60%, 80%, all this kind of stuff. Green, blue, red, and so on. And so on and so forth. So I'll describe Zooniverse now, but if you guys are interested in reading a bit more about this, it's a brilliant book, Digital Humanitarians. It describes the origins of the Planetary Response Network, written by Patrick Meyer, and it's quite a motivational book, really. There's no equations in it, and it's good for the that nighttime reading when you might be lacking a bit of motivation. Keeps you connected. So going forward, I'm going to try and recruit you guys in some kind of way to join us on this wonderful sort of journey through to saving the planet and saving people. That's the hope anyway. Right. So here's an example. Before I go into the details of Zooniverse, just tell you how we first used this thing. So there was the earthquake in Nepal in 2015, and we decided to go operational with Zooniverse and machine learning and so on and so forth. What did that mean? It meant getting satellite imagery from, in this case, it was Planet Labs, as it was called then. This was actually pre-disaster satellite imagery. We had that available. We went to Rescue Global and said, what information do you need? Actually, their response was, now's not the time to do science. No, we're not doing science. We're going to help you in this particular case. So they wanted to place water filters and life detectors. Okay, what does that translate into? Translates into population size. Well, OpenStreetMap, you get population size from that. They've mapped all the buildings and all this kind of stuff. Absolutely brilliant. But it's an incomplete map. It can be fairly old. We need something sort of that reflects here and now what's going on. So we took the Planet Labs data and then we crowdsourced it. So we put up, okay, let's go to the next, come to this thing. I'll demonstrate what this is about. This is it's a Zooniverse. Now, everybody can access this. You can go on your phone right now, you can go on your iPad and so on, and access this thing. And what you do is you create a project on here. You get a little introduction, describes what the project's all about, and then you get your satellite image. And it might be before and after. Oh, it's not showing. Oh, it's not very clear. It's very, very dark, isn't it? Oh, I see. Oh, it doesn't come up. Oh, what? What? That is weird. Okay, so if I get out, yeah, thanks for that call. If I get out of this, it worked before. Damn machines. There we go. Okay, so if we bring, oops, no, need to do that. Bum, 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 bum. Let's make that bigger then. Right, there we go. That'll do for now. So we've got before and after imagery of a disaster. And we asked people to label anything they see in there. So questions down the side: road blockage, flood, temporary settlement, structural damage. So you might spot road blockage, for example, maybe there. So you mark road blockage and then boop, mark it here. And then you move on. We asked people to label a whole bunch of different things in here. They might, I don't know, so see, structural damage perhaps. Boop, using before and after comparisons. Done. What this is giving us is a database that we can train a machine learning algorithm. Right, so let's go rid of that. Go back to this. So that's Zooniverse. So we got people to determine in these little sub-images that we gave them the degree of building, the number of buildings, whether this is hugely built-up area, and so on and so forth, around Kathmandu. In this first run, we kept everything in-house, so we used our disaster response guys and PhD students and all this kind of stuff. So we had, I think it was 25 people working on this. But very rapidly, we were able to create a heat map indicating where the population centres were. We folded in OpenStreetMap as well to augment that a little bit, but then we found that there were 2 villages that were not in OpenStreetMap. We told the disaster responders about this. They said everybody's using OpenStreetMap to decide where to go, and then they sent a reconnaissance team out to check on these 2 villages that they were okay. That was nice. Components of impact there, which was fine. More recently, we responded to the hurricanes in the Caribbean. So we got an answer to one of your quiz questions. $282 billion damage due to these hurricanes in 2017. That's absolutely huge. More importantly, 3,300 people lost their lives. Great. This was a sequence of hurricanes coming in one after the other. It's quite unbelievable. And this is only going to get worse with climate change. So our disaster response team was out there, and after each hurricane came in, they said, right, what can you tell us about this? What can you tell us about that? They were going from island to island hopping. So tomorrow we're going to be in St. Thomas. What can you tell us about St. Thomas? So they wanted maps generated like that, within 12 hours. I think 12 hours was the absolute limit we could deal with. And then we would hire the crowd, which would be you guys, and say, look, we need St. Thomas mapped right now. And then the crowd would start clicking away, spotting things on the satellite imagery and so on. And then ultimately, they might mark something like this, what you guys might do, a few little crosses on the damage there. Ultimately, we generate a heat map. And then that would be passed to Rescue Global in the form of paper maps, and also in the form of a kind of interactive GUI interface and so on and so forth. So, so we looked at sort of structural damage, there was roadblocks, there was flooding, temporary settlements. We saw people sort of building sort of shelters for the time being, and damage proportion and so on. And these are sort of the maps that we would send. I think we mapped about 10 islands eventually. So 300,000 classifications from 7,500 people over the time, covering 2,300 kilometre squared of islands. Each island was essentially mapped per day as our organisation was moving from island to island. If we would have had one expert working on this, it would have taken a year to generate these maps. So we were generating these things very, very rapidly, but just using the crowd at this point. And the kind of responses we got were, well, these maps are used to decide where to evacuate patients. And also, so SARAID used them to determine where to focus their attention in terms of damage, in terms of the area of interest, to then help the locals and so on and so forth. So we got some good feedback from these guys, and obviously the map was being used, or the maps were being used for good reasons. The maps were given to the UN, to FEMA, to 60 NGOs, and so on and so forth. So that's the impact side of what we're doing. So let's lift the bonnet a little bit and look at the AI. So crowd members are great, we value them tremendously, but some are better than others at labelling things and recognising what's actually going on in satellite imagery and so on. To begin with, we have absolutely no ground truth, so we don't know who's better, who's worse, but we use this idea of wisdom of the crowd. And you want to determine the accuracy of the members of the crowd, which is key, but you know that this Bayes methodology, which is the language that completely underpins machine learning, tells you what is the most coherent interpretation of the data and the most believable components of the model. So you're able to figure out who are the most reliable members of the crowd just by the way in which they cohere amongst the collective within the crowd, or of the crowd, and with the data that they have been presented with. And it's this idea of wisdom of the crowd. It's the most convincing members of the crowd who are determined to be the most reliable, that are ultimately the most reliable. That probably doesn't make sense. But anyway, so we use machine learning to figure out who are the most reliable members of the crowd. Then we can use that consensus to train a neural network. And that neural network can take the satellite imagery and respond to the questions that are posed about the disaster in the way that the crowd is responding to these things. So this brings us to something quite fundamental. Computers are incredibly dumb. Humans are incredibly bright. So humans can answer questions in terms of the context in which those questions are posed, and then the computer can just pick up on the patterns of how the humans are answering those questions in that context. And that's the key thing to what we're doing here. And so what you've got, okay, you've got the humans training the neural network, but then they're simultaneously both labeling the satellite data. So that means that as you get more and more and more labels, the neural net is improving, and eventually the neural net reaches the same kind of reliability as the crowd, and then the neural net can go off and label everything else, all the other imagery. So that's sort of the basic mechanism that we're deploying here. Called data fusion. We can fuse in other sources as well, and also take the reliability of those sources into account and learn the reliability of those sources in the context of the collective. Our maps have been verified by end users on the ground. Digging a bit deeper, what does that mean? So crowd members can label individual points on the map. That's fine. You can come up with consensus at each individual point. Then you can use the neural net to interpolate, so to try and infer what is going on the rest of the map that the humans have yet to see. You can represent, you've also got a model of uncertainty. So where the map is not very well covered, where the labels are still fairly uncertain, whether where the neural net is uncertain, you can represent that in map formation. But also critically, you can determine what the next best point is, or satellite image and so on, to have labelled that will give you the most information. So you can reduce the cost, you can reduce the time, all this kind of stuff, using machine learning to get your entire area mapped. Digging a bit deeper. Okay, so we have this wonderful language. I mentioned Bayes as a language. It really is. It's a consistent methodology framework for creating models covering the entirety of machine learning, including deep learning. We're still working on very efficient Bayesian methods in deep learning, but we're making progress all the time. This is called a generative model, or a graphical model. It's a very intuitive way of describing a problem in probability theory. And what you have are sort of variables such as S, this is satellite imagery. From that, you generate the idea of truth, of what's actually going on in the ground. From that, with the idea of the reliability of a member of the crowd, you can then generate the kind of label that a crowd member might use to annotate satellite imagery. So following those arrows, you can sort of generate the data, generate the output, generate the label from the underlying input data, which is satellite imagery, and so on and so forth. So we have satellite imagery plus parameters of the neural net, gives you what you think is going on the ground. The label is generated by a crowd member with this confusion matrix. So the confusion matrix gives you an idea of the reliability of the crowd member. So this is sort of saying that if there's actual damage, the crowd member labels this thing as actual damage 70% of the time, 30% of the time they get it wrong, and all this kind of stuff. But those numbers can be learned from the data, and learned from this idea of consistency and coherency and wisdom of the crowd. We also have a neural net. I won't go into that in too much detail. This is a fairly standard one. It's one of the oldest neural nets, deep learning neural nets with all the various layers and so on. And then results, we have this wonderful thing called variational Bayes, which does the whole inference, the whole learning stuff incredibly quickly. And as you can see there, compared to other methods, max likelihood and all this kind of stuff, which you may have heard of, this gives you far more accurate results, and also less uncertainty in what we've got. So if you want to read a little bit more about the technology underpinning this, there's a paper there, paper reference. I can give you this person later on if you want. We've also released the code if you want to play about with that. It's in Python and using TensorFlow for the neural net modeling and so on and so forth. That's all freely available. Right, what's next? So we're using this technology now to address some other problems in disaster management, environmental protection. The first thing we're looking at is we're working with Save the Elephants and also with the zoology department. First of all, to track elephants using satellite imagery. And secondly, to track these bomas. Now, bomas are farmsteads in Africa, in Kenya. They're sort of semi-nomadic things. They are farms. The elephants love what is actually grown in the farms. The farmers hate the fact that the elephants actually take what is grown in the farms. So there's that conflict, and elephants do suffer as a result along with the farmers. There's a nice kind of practical solution that some have adopted, and this is placing beehives around the fence of the boma. Elephants hate bees because bees get up the trunk. Farmers love bees because they get honey from them. So it's a kind of win-win situation there. But anyway, we're so we're looking at sort of the human footprint in that context. We're working with Earth Sciences in Oxford to identify seismic faults. So seismic faults, these are sort of, we're looking at perhaps below grade 7 in terms of the, I don't call it the Richter scale anymore, but I think you know what I mean. And these kill between 10 and 20,000 people every year. So people tend to build on faults, because where you've got faults, you tend to get breaks in the crust, and that's where water rises up, so you get lakes. People like to build next to lakes. They don't really know they're building on these faults, so we're trying to map these faults worldwide. We're having some success on that at the moment. Don't know if you remember the tailings dam that collapsed about 3 or 4 months ago now. That was the third one to collapse. The company that builds these things is supposed to be maintaining their health. Fortunately, since 3 have gone, the Brazilian government contacted them and said, look, can you help us, first of all, identify where these informal dams are, and then secondly, help us monitor these things. So this is another application where we're using this technology. Right, I'll leave it there. Thanks for your attention. I hope I've got grabbed some of your interests partway through that at different scales. If I've lost some of you, I'm sorry, but you have to try and cater as many as possible. Right.
I hear you. Your very last point. I believe that I read in the BBC that through looking at satellite pictures, there's a dam predicted to go in the next few days, using, I guess, the same sorts of technologies that you're talking about there. They reckon that it's slipping at so much, millimeters per day,
right.
and the prediction is that any time now another one's going to go. So
okay. Yeah.
I guess that's a very real world application.
That's right. It's very interesting. So you say that you can get the dam moving forwards and backwards due to the pressure of the water behind it, and that's not a problem. It's when the dam starts to twist. That's where the problem is. So some dams have got little sensors on board, and you can detect those things. They're also using, I think it's SAR, to monitor the movement. Synthetic aperture radar to monitor this kind of thing.
I think that's what they were saying. So, and I suppose it's all statistically analysed, and they can kind of tell from looking at the past and seeing what's actually happened there, and then this is how they can make this prediction. And this time they've evacuated everybody.
Yeah.
But as I say, when I read it, it was just like within a week. Yeah. I reckon it's going to go. So.
Yeah. There's lots of these things, and government doesn't know where the hell they are. So so it's a tricky problem. Yeah.
You have the people on the ground telling you when the mistakes are made, or?
Yeah. So the model's validated through feedback we get from people on the ground.
And does that validation feed back into the AI, or?
It certainly does. Yeah. So far we've only had positive feedback. But they are interested in broad brushstroke statements of where there is damage and so on and so forth. So fine detail. Now, what we actually find sometimes, it's quite amazing. You look at individual crowd labels, and you'll get a dot in the middle of the ocean. It's like, what's going on there? It's very rare you actually get a dot on top of damage. But when you look at the area where the dots are, it's where most of the damage is. So the dots are kind of, so there's a scale issue here, that we can't say that building is damaged, but we can talk about the general damage in that area. At the moment, although now we are deploying, or we're researching on transfer learning, where we get very detailed labeling by experts, certain locations, and then transferring that knowledge from event to event. to try and improve the accuracy, or at least the scale at which we can resolve damage and so on.
There was a very interesting point in your talk which I didn't understand, and I would really like a maybe more concrete example about the wisdom of the crowd,
Yeah.
where basically you're trying to determine which of these points are correct without knowing the ground truth.
That's right. So there's sort of Occam's razor. Familiar with that? It's you know, you always prefer the simplest solution or the simplest model. This is built in to Bayes' rule. So what you have to begin with is a very vague model, very vague set of relationships that connect together, you know, the crowd's reliability and the data and so on and so forth. And then you use Bayes' rule to find the simplest solution. And that simplest solution is the most coherent solution. So if everybody is saying it's X, the answer is going to be X. You know, if the majority are saying it's X, the answer is going to be X. If the majority of the people who are reliable are saying the answer is X, it's going to be X. You still have to work out who is reliable. Yeah? And, well, the majority is fairly obvious. But you get that all from the coherent stroke consistent solution by writing down the mathematics of Bayes. Yeah? Does that help? Yeah. Okay, cheers. Okay.
My question is more on the practical level. You were mentioning that the choice was to use the Zooniverse. And I was wondering why Zooniverse versus OpenStreetMap and how you see that moving forward, that relationship is really good.
Okay, so OpenStreetMap's absolutely wonderful, and I've been involved in their Hidden Maps project, which often takes place here in London, where you go along and they, you know, and you map buildings and all this kind of stuff, and halfway through they bring out pizzas, and you munch the pizza, and then that's the end of the evening because you're just chatting to everybody and eating pizza and so on. So what their interest is very detailed modelling of the world here and now. What we need to do is figure out what the world looks like immediately after a disaster, and the world's completely changed. So we haven't got the time to detail model, you know, this is what a collapsed building looks like and all this kind of stuff. We can't do that anymore. So we need to generate these maps really quickly. So we haven't got the opportunity to, you know, to bring people into London, give them pizza and all this kind of stuff. So the fact that Zooniverse is online, I'm sure OpenStreetMap, sort of hidden map stuff is now online. I'm sure they're doing that. With Zooniverse, we've got a huge crowd available. You know, essentially access to a million people who've done all kinds of projects on Zooniverse. So they're prepared to engage at very short notice, so at least we find a subset prepared to engage at very short notice. So we know we've got the crowd availability, we've got the platform development support, and we know it works.
So yeah, if you want to join me saying thanks to Steve.